Welcome to the Bodhi Academy. My name is Amsha Kulaso, and in today's video we will continue with our chapter class 12 chapter 3 chemical kinetics. So previously in this video we learned about the zero order reactions. Now today we will move ahead and we will learn about the first order reactions. Now in this class of reactions, the rate of reaction is proportional to the first power of the concentration of the reactant R. So what they are saying, for example, if we have reactants giving product P, so then the concentration of this reactant is raised to the power of 1. So here if we have to write the rate law expression, we can write rate equals to minus dr upon dt equals to kr. Also on rearranging, we can get the r terms together, we'll get dr upon r equals to minus kdt. Now on integrating this equation, we will get ln, that is natural log of r, concentration r equals to minus kt plus I, where I is the constant of integration. This can be also c or it can be I as well. So if it is the concentration constant of integration and its value can be determined from the graph itself. So now if we have t equals to 0, then r will be equal to R0, that is initial concentration of reactant R, where R is the initial concentration of the reactant. Therefore what we can do is, on substituting here, we will get ln R0 equals to minus k, t is we said 0 plus I, so ln R0 will be equal to I. So now substituting the value of this I in this above equation, in this equation, if we substitute the value of I, we will get ln R0 equals to minus kt plus ln R0. So now on rearranging the same equation, we can get the R and R0 terms together. So ln of concentration of R upon concentration of R0 equals to minus kt, or we can also write k equals to 1 upon t ln of R0 upon R. So now at time t1 from the equation, we can say that ln R1 will be equal to minus kt1 plus ln R0. So at time 2 also we can write a similar equation, just we have to change this subscript to 2's because now the time is t2. So now when R1 and R2 are the concentration of the reactants at time t1 and t2 respectively, on substituting we get this equation. Sorry. On substituting, we will get ln, that is we write initial concentration minus the final concentration, and same way minus kt1 initial time minus the final time minus k2. Now here k and k is common, so we can take it out. So ln R1 upon R2 will be equal to k t2 minus t1. So here on rearranging, we can say that k equals to, if we have to find just k, that is the rate constant, 1 upon t2 minus t1 ln of concentration of R, initial concentration upon the final concentration. So from this equation we can also write that ln of R0 upon R0 equals to minus kt. If we take anti-log for this equation on both sides, we will get this ln will go off and we'll have concentration of R equals to concentration of R0 e raised to minus kt. Now on comparing the equations with y equals to mx plus c, if we plot ln R against t, so we get a straight line slope with minus k and intercept that is equal to R0. So see here, if we plot ln of concentration of R against time t, we get a straight line graph with a negative slope and we have the intercept, that is the ln R0. Now for the first order rate reaction, we can also write it in the form of, by removing the ln, so we put the value 2.303, k equals to 2.303 upon t log of R0 upon R. So if we plot this now, if you have log of R0 upon R, if you plot this against time, the slope that will be equal to k upon 2.303. So now some examples of first order reactions are, first is hydrogenation of ethane. So in that we have ethane molecule plus H2 giving us C2H6. In that case the rate it will be depending on the ethene molecule. So all natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. Also decomposition of N2O5 and N2O are some examples of first order reactions. Now next, let's talk about the half-life of a reaction. Now what is this half-life of a reaction? So the half-life of a reaction, it is the time in which the concentration of the reactant is reduced to half of its initial concentration. So whatever the concentration was initially at half-life, it is reduced to half. So it is represented by T half. So now if we have a zero order reaction, we can write a rate constant K equals to R0 minus R upon T. So now at time T equals to T half, we can say that R will be equal to minus 1 upon 2 R0. So the rate constant at T half becomes K equals to R0 minus half R0 upon T half. So now if I have to just write a T half equation, I will rearrange this. This T half I will take here, and this R0 I will take out common. So on taking out common, I will get this R0, and here I will have 2K. So now from this equation, it is clear that T half for a zero order reaction is directly proportional to what? The initial concentration, that is R0 of the reactants, and it is inversely proportional to the rate constant, because here see we have K, that is the rate constant in the denominator. So if T half is increasing, this will reduce. So therefore they have an inverse relation between both of them. Now if we do the same for a first order reaction, we have K equals to 2.303 upon T log of R0 upon R. So here at T half, R will be equal to what? Half the concentration of the initial one. So R0 will be divided by 2. If now we substitute here, this we are going to substitute in this above equation. So on substituting, so if we have K equals to 2.303 T half log of, we have here R0 upon, now this R we are substituting by this. So we will have R0 upon 2. This if I take reciprocal, here this part I will get log R0 upon R0 into 2. So this R0 and this R0 will get cancelled. So we will be only left with log of 2. So T half will be equal to 2.303 upon K log of 2. So T half can be written as, on substituting the log value of 2, that is 0.301, we get T half equals to 0.693. Now it can be seen that for a first order reaction, the half period is a constant. That is, if we see in the initial, for zero order, we saw that it was depending on the initial concentration. Now here if you see, we are getting a constant. There is no concentration of initial nor any final reactant. So in this case, we can say that it is independent of the initial concentration of the reacting species. The half-life of first order reaction, it is readily calculated from the rate constant and vice versa. So for a zero order reaction, we can say T half is directly proportional to R0. For first order reaction, T half is independent of R0. Okay, so these are the two observations we can make. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.